Hi everybody, we're continuing section, what's that is, 4.3, and we are, this is part two. So let me jump right in and share my screen with you because in part one, we spent a lot of time showing how to take a second derivative, in a two variable function. And how to, you take a derivative with respect to x and then a partial, either a second partial with respect to x or a second partial would be with respect to y, and so on and so forth. We went through this, at length in the previous video. But the question we never really got into was why is any of this even important? What's the relevance or significance of taking these derivatives in one or two derivatives in excuse me in three-dimensional space in or as we say a function of two. By the way, we say you ever notice? Actually, I think I'll make a discussion of that. Okay, never mind. I'm gonna. I think in one of my discussions, I'm gonna say how come we call it a function of two variables, and that's three dimensions. But it's a function of one variable. It's a two-dimensional thing. It's on the plane, XY plane. Um, that's a good discussion question. I think I'm gonna bring that up. Okay. I'm not gonna answer it now. I'll see what you guys have to say on that. Anyways, let me share my screen and we're going to get into some mathematics. Okay, so I want to start with just a definition here. Local maxima, minima, and saddle points. Now the idea of a local max and a local min, that's something we've seen before, in the regular XY plane. We've never seen this, at least not yet. We've never seen this idea of a excuse me, a saddle point, but live and learn. So here we go. Let me get my picture out of the way. Uh, so here we go. As you remember, a local max, that means the greatest value in that local area. Local min is the lowest value or the least value in that, you know, we know that local max and local min in a regular one, what regular, regular two-dimensional calculus or calculus of one variable. We know that it only happens at critical points and when the derivative is either zero or undefined. And we also know that not all critical points are maxes and mins, and we need to test them. In till now, when we're dealing with functions of one variable, uh, so we use the first derivative test, the second derivative test, and so on and so forth. And now we're going to look at functions of two variables, which, as I said, takes place in three-dimensional space. When you graph it, it's a graph in three-dimensional space. So what we're going to find that the ideas that we learned in just good old functions of one variable, those ideas though are going to still hold. They're going to have to be modified and tweaked, to work, to adapt to this new situation. But the basic concepts is, and the truth is, that's the way it is with calculus. Once you learn the basic definition of limit, the basic definition of derivative, which we did a long time ago now, it seems like a long time ago, even though it was really, just weeks or a few months ago. Once you learn there, then everything else is just applications of that. It really, that's the concept. And now we're taking that concept that we did in two dimensions. Now we're applying it to three dimensions, and so on and so forth. And we could apply it to, if we wanted to, we could apply it to four dimensions, n dimensions. But let's just take one thing at a time. So let's just look at a definition. If you notice, this definition really kind of parallels the definition we had, originally. Uh, so let's just read it in this nice little yellow box here. So I can't guarantee this is made out of brick. Then it'll be a yellow brick box, and I would see Dorothy and Toto and all of them. But at least it's yellow. Anyways, F has a local maximum at the point A comma B. See, before we said when X equals A. Now we're saying when X comma Y is equal to A comma B. So if the value, when a two-dimensional function means I put in two variables, I put in the X variable and the Y variable, and it spits out a number. Just like a regular function, you put in one variable, spits out a number. Here you put in two variables, spits out a number. So if that spit out number is greater than all the other spit out numbers, all the other, for all the points that are near A comma B, then A comma B is a local max. And on the flip side, if the function value, the number that gets spit out for a comma b, if that is less than all the function values around in the vicinity of a comma b, then that's called a minimum. Really, it's the same definition we had with one variable, function of one variable. It's just now it's a function of two variables, but it's the same, really the same idea. So, like I say, we're just sort of taking the concepts that we established and now applying them in more dimensions, more variables. Anyway, a critical point is a point where both of the following are true. Either the partial, I'm sorry, not just either, but the partial of x, in other words, the partial derivative of the function with respect to x is either going to be zero or undefined, and also the partial derivative of the function f with respect to y is also going to be zero or undefined. And I'm really just reading what it says in the yellow box. And just as we had with the one variable case, a local max or a local min can only occur at a critical point. Now, and also we're going to find, sadly, that just like in the one variable case, not every critical point is going to automatically be a local max or local min. The first derivative test and the second derivative test that we did back then, that we can't do that here. That was only defined for one variable, but we will have a similar type of test. And that's really what we're getting to now. So I'm going to scroll a little bit. I'm giving you the theory now, and then we're going to do a whole bunch of applications and just show you how this stuff works. What just happened here? Let's try that again. Okay, now it's going nice. What happened? I jumped a little bit. All righty. Now, here's interesting. I want to show you something. There's something called a saddle point. And if you look at this, this is a graph. So the function here is f of x comma y is equal to 5x squared minus 3y squared plus 10. And if I would graph that, again, you need three-dimensional graph paper. As I said, I very highly recommend GeoGebra for three-dimensional graphs. And so this point right here, if I could, the point right at that point right there, that point right there, we'll see those two lines intersect. That's called a saddle point. Because if you look at it from the top, it's kind of a min. But if you look at it from the bottom, it's kind of a max. So what is it? A min? It can't be both. It's got to be one or the other, but it's sort of contradictory. So it winds up not being a min or a max. And that's an example. Yet that point is a critical point. That point is a critical point. Okay, let's so I'm sorry, I just lost something here. You might be wondering, what is this point? That point, that saddle point. Where is it? What is it? What point is it? Out in space. So let's do some calculus. Let's do some calculus. Before I do the calculus, I'm going to show you it on GeoGebra. Then I'm going to work it out why it works out with the calculus. So let's do that. Let's see. GeoGebra is right here. And I'm going to type in. Now, by the way, we use the letter Z. Z is equal to, this was our, instead of f of x comma y, we use the letter Z. And this is the function. Wow, it's really big. So how do I get? No, I don't want to. Oh, okay. So that's all right. So this is what it looks like from the side. This is what it looks like from the other side. It's kind of like paradoxical in a way. But this point right there, that's our saddle point. So where is that point exactly? Well, I'm gonna give it away, and I'm gonna just put the point in right now, and then I'm gonna explain how I got this. 0, comma 0, comma 10. And oops, it would be nice if I put it inside the parentheses. There you go. And it's see that there's a point A right there. And it's right at A is right at that saddle point. A is right at that saddle point. Uh, I really love this site. You can just play around with things all day, but it's really it's on the z-axis. It's on the z-axis. And you can see right there the point. Okay. You're looking at a slightly different angle. If you see there, you'll see more how it's exactly on. Anyway, so there you go, right on the z-axis. So let's see where we got that from. So I'm going to switch cameras. Let's see. I'm going to stop the share, and I'm going to switch cameras. Switch right now. I'm going to show you how I got this. How I got this point. So let's see. 2 point blah blah. Let's go to my camera. Here we go. But somebody may have noticed that my finger is bent. This finger right here is bent. It's actually an injury I got when I was in high school, of all places. And I was playing baseball and I kind of jammed my finger, and I didn't realize it was broken until it just kind of healed itself, kind of reset itself eventually over time, and it came in like crooked. I just never felt it was important enough to have to fix it. I guess I could have them re-break it and refix it, but I never did. Anyway, if you consider that too much information, then that's a good sign that you're normal. Weird with me. So let's move on. What was our function? Function was to recall the court's memory. F of x coming over to c would be the two f of two is the same is equal to and we'll equal to 5x squared minus 5x squared. So what will the x and the y well? Well, here these are real constants. That's y on the other hand. Well, that's a constant. That makes and point of negative y is 0 undefined. Point of well, it's never going to be undefined. 10x is just a polynomial, and they're never undefined. Negative 6y is just a polynomial, not undefined, but it's equal to 0. So if 10x equals, if I set this equal to 0, I get x equals 0. And if I set this sucker equal to 0, I get y equals 0. Really, it's 0, 0. What is the z value? What is the z value? When we get the z value, we have to plug in the x and the y, and get it that way. So I'm going to look at f of z equal to 5 times 0 squared minus 3 times plus 10. Now, of course, this is 10. And that's why I typed into the algebra 0, comma 0, comma 10. That was my answer. So that was the right stuff. And that is lovely. Okay, let's move on. I want to go back to let's see. We need to go back to the other camera. Let's continue. Let me share my screen. Here we go, sharing the screen. And I want to go through this test. This is the test. And we're going to do a whole bunch of examples of this. But for now, I just want to look at what the test is. So this is the second derivative test for functions of 2 variables. So before you apply the test, you have to make it simple. We're gonna ask you to compute something called d. So D is fxx times fyy minus fxy times fyx. There you go. So whatever the function is, we take we take the second derivative, which is where we're doing two x's, then the second derivative that does two y's, the second derivative that does x first and then y second, and times, and then here we have the one that does y first and x second, and we multiply it together in this multiply and subtract in exactly this fashion, and we get this value, we get this d. And it says here, evaluate it at each critical point, meaning that we're going to plug in the example we had done, we're going to we would plug in whatever this comes out to be. This is going to be something, and we would then plug in the x value and the y value that we got. But let's just look at what the test is before I show you how to use it. So if d is positive, so there are three possibilities. D is going to be some number. When I work out this this whole thing here, this whole expression, I don't know what you want to call it, and then I evaluate it by plugging in the x and y that were the critical points. So I'm going to get some number because I'm actually putting x and y values into this new d function. So that number that I get, if that is a positive number, then that means we have a local max or a local min at the critical point. If it's a positive number. But which one is it? Is it a max or a min? Well, if in addition to d being positive, fxx is also positive, then we have a local min. If in addition to d being positive, fxx is also negative, then f has a local max at that point, at that critical point. And that was case A. That was when d is positive. Case B, if d is negative, then f is going to be the saddle point at a critical point, and the saddle point, as you know, is it doesn't have a max or min. And finally, if d is equal to 0, then the test is inconclusive. Could be max, could be min, might be neither. Anything is possible. So d is negative, definitely no good. It's a saddle point, which definitely is not a max or a min. If d is 0, it's anybody's game. But if d is positive, it will be a max or a min. And whether it's a max or min depends on the fxx, whether that's positive or negative. And that is the test. That is the second derivative test. So it's similar. It's a little bit more involved, than which is not so shocking that a three-dimensional scenarios, function of two variables is going to be more involved than a function of one variable. But that's what we got here. That's what we got. So it all works out very, very beautifully. And so, by the way, this reminds me a little bit of our functions of one variable, because when the second derivative, and there we're only talking, and there we're talking about y equals f of x, both derivative in the regular case. So the function of one variable, which is the regular xy two-dimensional case. So in that case, when the second derivative is positive, that means it's concave up, and we have a min. And when the second derivative is negative, it's concave down, which means we have a max. That's kind of interesting. That is kind of, again, this very much parallels the two-dimensional case. So that's kind of interesting, kind of fascinating. Anyway, this is the test, and we're going to put it to some good use. But we're going to do that in the next. Oh, actually, I'm sorry. I want to do one example. I want to continue with the saddle point that we just had, that we were just working on, and then I'm going to end this video and make a part 3, which will have more, examples and stuff like that. Okay, I'm going to go to my paper now, and let me just write down here. So I'm going to go to my paper, and I want to go to this camera right here. All right, and not okay. So we want D D is going to be fxx times fyy minus fx times fyx. So here's our function. Let's get a little. Let's find. So no fx, no fy. Fxx is going to be fy going to be fxy. Well, that's just going to be zero because if I take the derivative of this guy right here with respect to y, it's just a constant. So this is zero, and fyx at the same time is also going to be zero. And how do I know fyx is zero? You don't have to look here. It's just the same thing. You take the derivative with respect to x of x here. Or, if you remember, we mentioned that if x1 and fyx are always going to be the same thing immediately, so d is going to be equal to this. Well, it's going to be 10 times negative 6. And that's negative 60. And the last time I wrote, negative 60 is less than 0. So d is less than 0, which means, please, saddle point. And that is that. Well, I'll make another video, which is going to give more examples and get it and get into some more fun. And I will see you guys. Okay, everybody. Bye. That's my arm, by the way. Bye.